But this problem begins the first in a set when we're going to still be doing free fall motion, but we're going to initially start by throwing an object up, and then it's going to reach a maximum height, and then it's going to start to fall back down. Later on, we'll have rockets that'll actually accelerate an object up, and we'll get to those later. But here we do have a couple of problems where we're throwing something up, and we're trying to figure out where does it get to its maximum height, and then what happens as it comes down into the bottom here. So I'll read the problem, and it's a good problem, but one thing I want to do before we get there is you can use some of your intuition from everyday experience in these problems. The first one is, if I were to have an object like this marker, if I throw it up and it reaches some maximum height before it comes back down, there's a couple things you already know from living on Earth that you can apply into these problems. The first one is, however long it takes for this marker to reach its maximum height, the time that it takes to reach the top is exactly equal to the time it takes to fall back down to its initial position, right? So if the initial position is here, let's pretend that I throw this thing up and it takes 1.5 seconds to reach the top. Then because of symmetry, you also then know that it takes 1.5 seconds to get back down to where it started, right? So that's something you can actually use to help these problems. And then the second thing I want you to kind of keep in mind is something you already intuitively know, is that if you launch this thing up with a certain velocity, let's say we launch it up at 10 meters per second, then it's going to reach a stopping point and then it's going to accelerate back down. At the moment that this marker passes through or reaches the same place you started from, its downward velocity will match exactly what you started with throwing it up. So if you launched it up at 10 meters a second, by the time it comes back down, when it gets down to the same spot, it's going to be going down at 10 meters per second. So those two things can actually help you solve quite a bit of problems. If you just remember that the time going up must be equal to the time getting back to the same spot, and the initial velocity you throw it back at it's going to reach a height, and then it's going to accelerate back from 0 at the top back down to the same velocity but going in the other direction, that can help you. So keep those two things in mind as we solve this next problem. It says we throw a rock straight up at 20 meters a second from a building that is 50 meters tall. We want to find the following things. Part A, what is the time needed for the rock to reach the maximum height? In other words, when it stops and then it starts to go back down, how long does that take to get to the top of to max height? Number 2, what is the maximum height above the throwing level? Because you're standing on a building, right? So you want to know in this part B, what is the maximum height above the throwing level? In other words, from the top of the building. Part C, what is the time that it takes for the rock to return down to your level, wherever you threw it from? The next one, what is the velocity of the rock as it passes you, where you throw it from? And part E, what is the velocity and position at t is equal to 5.0 seconds? So there's a lot of stuff here. Even though it's a simple problem, you throw a rock up and you want to basically find out what's going on, we still have to draw a picture because it's going to make it a lot easier. So the very, very first thing we're going to do, other than writing our equations down that we've been using, is we're going to draw a building. And as you can probably guess, my building is not going to be a very complicated building. My building is a nice rectangle. Okay, if you want some windows here, we'll draw some windows, you know, whatever, we can do that. But essentially this building, it tells you in the problem, it says we're throwing it 20 meters a second from a building 50 meters tall. So this distance is 50 meters. That's going to be useful. And then we're going to be standing at the top of this building. We can draw ourselves right here, happy face, standing right on top. And it says we throw the rock straight up. So in reality, we're throwing it straight up. It turns around, or it stops, I should say, and then it comes straight down. But in order to draw it clearly, I'm actually going to draw it like this. We're going to say that this is the throwing level, even though my hands are really up here. This is the throwing level. But what's going to happen is I'm going to throw this rock right here. And what is that trajectory of that rock going to do? It's going to go up like this. It's going to slow down, and then it's going to reach a maximum, and then it's going to come down like this. So it's going to initially go up and then down, down. But when I draw them like this, you need to know that really it's going straight up, and then, well, I should do it like this, straight up, stopping, and then coming straight back down. The curved part of the path is not really real. It's just to help me draw it for you so that you know it's going up and coming down. All right, so let's draw a couple of additional things. So here, when we first throw the rock, right, I'll do this. What is the initial velocity? The initial velocity is given in the problem. It says you throw a rock straight up at 20 meters a second. 20 meters per second. Now, We chose a positive sign on 20 meters a second. Why? Because we're throwing the rock up, and up is always, or typically going to be taken as a positive direction, positive velocity, positive position is going to be anything above the starting point. Negative velocities is when you're going down in the down direction, and negative positions are anything below this point. So if this is our throwing point, typically we want to say that the initial position, why not, we're going to call this the 0 mark. The dotted red line here where the rock starts from, that's 0. You don't have to do it this way, and there's lots of other ways you can do the problem. But typically when you're throwing objects, starting motion from a certain position, you want to take that initial position where you're launching the rock from as y is equal to 0. Anytime the rock goes above that point, it'll be a positive position, positive y, a positive distance. And anytime the rock gets down below this initial position, like anytime down here, it'll just come in as a negative distance. Like -5 meters would mean it would be 5 meters down below the launching point. Now for the velocities, anytime the rocket's going up, it's positive. Anytime the rocket's coming down, including way up here, anytime it's traveling in the negative y direction toward negative y, we call it a negative velocity. Now, the special point up here that you need to take note of is at the very top. Because at the very top, there's something very special up there. We call this the max height. And at that point, we know for sure that the velocity of this rock is equal to 0. Because it's going up, 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 slowing down, and then it must reverse direction. So at that moment at the top, the velocity of the rock is 0. That's actually going to be useful. You can put it into these equations because that's the constraint at the top of the place there. And then, of course, at the very top, one of the questions we're asked for is what is the maximum height? So at the top of this guy is going to be a position called the max height. And then, of course, at that point, you have a velocity of equal to 0. So I think we have pretty much everything written down. And now we're going to tackle one part at a time. It says, what is the time required to reach the max height? So you're going to need to find an equation that involves time that has all of the other variables known. Right? So we know, notice it says max height. What do we know max height? We know the final velocity of the thing is 0 here. In other words, yes, the rock does continue to come back down, but if you consider this launching point to be the initial velocity, we know it's 20. If we consider the motion to be completed at the top, we know the final velocity is 0. So we know both of these. We always know the acceleration of gravity, which is -9.8. So we can calculate the time required to reach the top by knowing initial velocity, final velocity, and the acceleration. So we're going to use this equation right here. And the way we do that is to solve part A. We say that the velocity is v0 plus the acceleration times the time. The initial velocity we know, that's the launching velocity. The final velocity at the top, we call it 0. The initial velocity, we call it +20 because it's going up. You have to get the signs correct. If you were, for instance, to be at the top of the building and throw the rock down, then the velocity wouldn't be 20 meters a second. It would be going down. It would be -20 meters a second. And then the problem would be completely different. In this case, we're launching it up, so it's a positive velocity. Then we have plus, what is the acceleration? It's always -9.8, negative because it's acting downward, which is contrary to the upward velocity, times time. Okay, so when you solve for time, you're going to move a 20 over here to be -20 over -9.8. So the time that you get when you divide those numbers, you get a positive time, 2.04 seconds. So a lot of students get confused with these problems because you're given a lot of information and a lot of things to find, A, B, C, D, E. So you just take it one step at a time. I know the initial velocity, I know the final velocity. Now when I say the final velocity, of course we know the rock continues to go down. I mean, the trajectory continues to happen. But in this window of time, only looking from launch to maximum height, the initial and the final velocities are known, the acceleration's known, so it's just a fixed amount of time required for gravity to slow it down up to a velocity of 0, and that's the time that we have. Now the second part says, what is the max height above the throwing level? So what that means is you want to figure out what is this distance above the throwing level. Now you got to be careful about how the problem is worded, because if it says what is the maximum height above the ground, then you know that you would have to find this height, and then you would have to add 50 to it because the ground is way down here. But the problem doesn't say that. It says what is the maximum height above the throwing level? The throwing level is here at y is equal to 0, and up there is where we want to figure that out. And now that we know that this distance that's traveled to the maximum apex actually takes 2.04 seconds. So we want to figure out what is the max height. So we're going to use this equation because we want to figure out what y is. We know the initial position, we know the initial velocity, we know the time, and then we know 1/2 at squared. We know the acceleration, we know the time. So we know everything on the right-hand side. So what we have is part B, y is y naught plus v naught t plus 1/2 times a times t squared. So we want to find out what is this final position, for lack of a better word, at the top of the apex there. So that's what we're trying to find. The initial position is 0. The initial velocity is positive 20. But now we know that the motion to the top of the apex takes 2.04 seconds plus 1/2. The acceleration is always negative 9.8. And t squared is 2.04. So we'll square it. So what you get is this term multiplied together gives you 40.8. All of this stuff, when you square this, multiply the negative sign, makes it a negative 20.39. And so the distance y, or the position y, is 20.41 meters. So what this means is that at the apex, the very top, right up here, it's 20.4 meters above the throwing position. If your problem said, what is the maximum height above ground level, you take that number and you'd add it to 50. So you would get 70.41. All right, now let's read part C and let's think about it carefully. Part C says, what is the time for the rock to return to your level? When you have something phrased like that, you need to go back to your picture. We go up, we reach a maximum, we come down. This is the same level we started from. So how long does it take the rock to go to this level, right? Well, this is when I talked to you at the beginning of the lesson about you can use a lot of your common sense. You know that the time required to get to the top of the apex is the same as the time required to get back down to where you started. You always know that because throwing rocks up, what goes up must come down. As long as there's no rocket engine providing thrust and it's just an initial velocity that you're throwing something with and it comes down, the time to get to the top is exactly equal to the time that it takes to come back down to where you started. So the very simple way to do this problem is to just look and say, well, it took 2.04 seconds to get to the top, so we'll just multiply that by 2. So we could say the time is 2.04 plus 2.04, so the time is 4.08. And that's correct, but it is the correct answer. But it's using your intuition to get to the answer. So it's great that you have that intuition, but it's not really the best way to solve a physics problem. To solve a physics problem, you want to use your equations to calculate the time. So if we were gonna, let's keep this here, because it is correct, but if we wanted to use the equations to calculate how long it takes to get back here, how would we do that? Well, there's always many ways to do it, but we can use this equation here and solve for the time required for the position of the ball to get back down to the initial position. Let's write the equation down and you'll see what I'm talking about. It's not a very hard thing to do. So the equation for position is y naught plus v naught t plus 1/2 times a times t squared. Now what we're basically saying, when the problem is phrased, how long does it take for the rock to get back down to the starting height? What it basically means is that at the initial part of the motion, the position of this rock is at 0 meters. We're calling y naught 0. This is the 0 position. It goes to some maximum height, and then it gets back down to where? To 0 meters again. So it sounds a little weird, but what we really want to do is we want to figure out how long does it take for this rock to get back down to the exact same position it started from. So that means the final position of the rock we're going to put in at 0 because that's the starting position. The initial position of the rock we'll also put it at 0. And then we have to fill everything else in. So it would be 20 for the velocity, initial velocity going up, times t, that's what we're trying to solve for, plus 1/2 times a times t squared, so we put negative 9.8, and we have t squared here. So essentially, you're just literally putting the final position to be the same exact thing as the initial position. So even if you're a little uncomfortable, let's just kind of crank through it and see what we get. We get 0 is equal to, here we have 20t, and then over here we have a negative 4.9 t squared. And you have to use your skills from algebra to solve this. What I'm going to do, just to make it this is the way I did it in my notes. You don't have to do this. I'm going to move these terms to the right-hand side just to make this positive. So it's going to be 4.9 times t squared minus 20 times t is equal to 0. All I did is take this and move it over, and then I took this and move it over. That's why it became negative. And we're going to solve for t. But notice you have a t in both terms. So what we can do is we can factor out a t, and then we'll have 4.9 times t minus 20 is equal to 0, right? You have a term. This times this gives you this. This times this gives you this. Now, when you have it set up like this, there's two solutions. The first one is that t is going to be equal to 0 because you have this times this is equal to 0. So this can be equal to 0, or this guy, the 4.9 minus 20, can also equal to 0. Whoops, not 4.9, 4.9t minus 20 equals 0. So you have 4.9 times t is equal to 20, moving the 20 over. And then when you divide by 4.9, 20 divided by 4.9, what do you get? 4.08. That sounds familiar, isn't it? But then you say, wait a minute, I have two solutions. Which one's correct? I mean, obviously this one matches what we got before from our common sense. But why did we get two solutions? Well, it's because in math, when you have any equation with a quadratic term, like a t squared or an x squared or whatever, you're always going to get two solutions. But oftentimes, one of them is nonsense. In this case, we're saying option number one is it takes 4.808 seconds for the rock to get back down to where it started. And then choice number two means t is equal to 0, which just means that's the exact moment I launched it. So what we basically found from the math is that there's two times that the rock comes back to its position. The first one is kind of like trivial. It just means t is equal to 0. Before I actually launch the rock is where it is back to the starting position. And the second one is 4.08 seconds later. So because we don't care about this trivial solution, we just cross that one out, because that's just basically saying at the time that we start everything, the rock is where it starts from. I mean, that's just trivial. It's valid mathematically, but it doesn't help us for our problem. So 4.08 seconds is the answer to that, and it matches with what we talked about before. All right, the next one says, what is the velocity of the rock as it passes you? The velocity of the rock as it passes you. So it goes up to a maximum, it comes back down, and now we know that that motion to get back down to where it is 4.08 seconds from the launching time. And we want to know its speed here. So we look back here and say, what are we going to use for speed? Well, let's use this equation, because I'm going to calculate the final velocity. I know the initial velocity. I know the acceleration of gravity. And now I know it takes 4.08 seconds for it to get back down here. So that's going to give me the velocity at that time. So to figure this out, you just say, for part D, you say, so what we have is our trusty velocity equation. V is equal to the initial velocity plus acceleration times the time. We want to find out the velocity at a certain time in the future. The initial velocity we know is 20, that's pointed straight up. The acceleration is negative 9.8, which is going down. And the time for that to happen after it goes up to the top and back down to the starting point is 4.08 seconds. So we're basically figuring out what is the velocity 4.08 seconds into the future. So when you take 20, you multiply these together, of course you have a negative sign, you end up subtracting those guys. What you're going to get is a velocity of negative 19.98, and of course when you round that, it's going to basically equal negative 20 meters per second. Why am I rounding it up? Because what we're basically figured out is that after the thing gets back down to where it started, it's going down, that's why there's a negative sign, of 20 meters a second, which exactly matches our initial velocity pointed up. So it kind of talks about exactly what we said in the beginning of the lesson. When you throw something up, the upward initial velocity is going to exactly be a mirror image of the downward velocity when it gets put to the same point, 20 meters per second up, negative 20 meters per second down. And notice that the signs took care of themselves. I didn't have to think. Well, is it going to be negative or positive or whatever? I just have to make sure and put the correct signs in of everything to begin with. Gravity acts down, initial velocity acts up, time is always positive, and I automatically get a negative velocity, which means it's going to be telling me if it's going up or down, which matches with what I know should be true. All right. Last part, what is the velocity and position of the rock when t is equal to 5 seconds? So you see, now we know that the motion of the rock at 4.08 seconds takes it back to where it started from. So the last part of the problem is basically saying, hey, after it passes this point, it goes a little bit below this, what is the position and velocity going to be? So after it kind of goes past our initial position, where we started from. So ask yourself before you do any calculations, are those position and velocity numbers going to be positive or negative whenever they pass the initial position? Well, if the rock goes down below where it started from, it's going to be moving down, which should mean they have a negative velocity. And the position of the rock should be below its starting point, which we're saying is negative. So we expect negative numbers for both of these. Let's see what we get, all right? And it turns out for both of these, we're just going to use the same two equations we've been using all along. Here's a velocity equation, a position equation, and we're just going to plug in the correct times there. So here we have part E. Try to switch colors, break it up a little bit. At time is equal to 5 seconds in the future. We know that this is always true. V naught plus A times T. So what is going to be the velocity in the future? 20 meters per second up is my initial velocity, negative 9.8, and then the time is 5 seconds. So I'll just stick a 5 in there. And then what I'm going to get is going to be, when you multiply these, subtract it from the 20, you'll get negative 29.0 meters per second, which is negative. It's a velocity going down, means it makes sense because the rock is traveling in the down direction. And then what is the position at 5 seconds? We're going to use our position equation, y naught plus v naught t plus 1/2 a t squared. So what is the initial position? 0. What is the initial velocity? 20. How long am I looking in the future? 5 seconds in the future. Plus 1/2. What is gravity? Negative 9.8. And 5 seconds in the future. All right, so what I'm going to have here, 20 times 5, is going to give me 100. And then I'm going to be subtracting off a term here. This will be 25 times this divided by 2. So what I'm going to get is 122.5. And so what I'll get finally is going to be, notice I'm going to subtract, I'll get a negative 22.5 meters, which is exactly what I predicted. The position is negative and the velocity is negative. The position being negative tells me it's 22.5 meters below my reference position, which is my 0 position. Anything lower than that means it's below that, 22.5 meters down, and the velocity is 29 meters per second in the down direction, which means it was negative. So there are many, many ways to do these problems. I mean, a lot of people in the beginning like to do this kind of thing. They'll throw it up, they'll figure out where the maximum happens, and then they'll just forget about the rest of the problem, and they'll start a new problem and say, well, I'm now dropping a rock from this height, 50 plus whatever, I'm dropping it, and then I'll just calculate where it goes along the way. And you can do it that way, that's fine. But I wanted to show you that as long as you know the initial position and velocity of that rock, you put the proper signs in, you don't have to worry about if it's positive position, negative position. It's going to take care of all of it. You're going to get an answer because on the upward traveling, on the upward part of the motion, gravity is still acting down, constantly slowing the thing down. But once it finally slows to 0, gravity continues acting on the object, pulling it with now with its negative velocity because it's now going in the negative direction. And when it passes its starting point, the position will then be negative, showing you that it's below your starting point. And we'll see that over and over again as we do these problems. I recommend that you let the signs take care of themselves in the problem. Don't overthink it too much. So solve this one yourself. Follow me on to the next lesson. We'll get some more practice with free fall motion. Learn anything at mathandscience.com.